I hope everyone had a great midterm too. I haven't really looked at your score yet, but I mean, if you survive my problems, you should survive the exams. So, yeah, now we're gonna get started with the materials of final exam. In my opinion, in Mat 141, this is like the most challenging part of materials, but the way that you like solve these problems is gonna be very procedural. So there's only one kind of method you're gonna apply for all of the problems, but then the understanding behind that is a little bit hard to get. So today we're gonna have the four, in my opinion, the four hardest part of final exam materials. So it's 11.8, 11.9, and then 11.10 and 11. So first one is 11.8 power series. So the power series is defined as the series of Cn, which is the coefficient in front of every term multiply xn, with n starting from 0 to infinity. Now, power series is just, the way that we learn this one is that we're trying to represent like functions like maybe exponential or sine or log, those kind of functions that we think that's really easy to find. But to put it in the way of power series and try to actually, approximate it, this is the way calculators work. So they don't, the way that they approximate a function and maybe like try to find the values of maybe say exponential of 2 in the calculator is using power series, where they put the exponential functions in the like in the functions of a lot of powers, so say like c0 plus c1 x2 1 plus c2 x squared, some things like that, and then they're gonna plug in the value maybe x equal to 2 or something, and then we're gonna find what is the value of exponential of 2 using this approximation of the power series. This is also it has a domain be the set of all value of x in which the series converges, and so kind of like basically saying the power series makes sense on its domain and it's the interval where the series converges. And so if you have all of the value of the coefficients, so say Cn, all of the Cn's is equal to 1, then you're going to end up with a geometric series. And this one is going to be converges when the value of x is between -1 and 1, and diverges when the absolute value of x is bigger than or equal to 1. We also have the concept of power series centered at A. So instead of x to the n, that is where we can rewrite as a series of Cn x minus 0 to the n. Then that one is where you say the series is centered at 0. But then instead of 0, if you replace it with A, then we're gonna have the series centered at A. And so the difference between these two is your interval of convergence. So if you have center at 0 and you have maybe the radius of convergence is 2, then you have the interval maybe something with -2 to 2, and you can include like this or like that, or all kind of possibilities. But if you have is equal at A, then your interval convergence is going to be A minus 2, A plus 2, and then a bunch of things with the bracket. So yeah, so that's the difference between center at A and center at 0. We also have a theorem for a given power series. It's saying there are only 3 possibilities. If R is not 1, then there be. Do you mean if R is not 1? Wait, hang on. What do you mean equal values? And what is R here that we're saying? Are you saying R is the radius? Okay. Do you mean then there'll be equal values? No, I mean I mean, that one is where you have the center as 0, right? So if you look at the interval from -2 to 2, what is the center of that interval? 0. But if you say you have a equal to 3, then this interval is going to become 1 and 5, right? And then this interval going to have a different center, which is 3. But here, if you have -2 to 2, then you have the interval with that center, with 0 be the center. You see what I'm saying? It doesn't really have anything to do with R. It more have things to do with the center. Okay, so now we have the theorem for any power series. There are only 3 possibilities. First one is converges when x equal to a. So it only converges in one situation when x equal to a. And that usually happens is that when x equal to a, when you plug in here, every terms will become 0. Yes, that's true. That's gonna be one of the steps that we're gonna, yeah, it's gonna be the next slide. And then it converges, either converges for all x in R, and you're gonna figure out if you're gonna figure out what value of R. So in this case here R is 0. So the radius of convergence is 0 because the series only converges at one point at x equal to a. But here if it converges everywhere, your R is gonna equal infinity, and you're gonna figure out what value of R your situation is looking for using the ratio test. And then the last possibility is that you have an radius of convergence such that the series converges if x minus a is smaller than r and diverges if x minus a is bigger than r. And as you say, if we're gonna take x minus a equal to r or not, x minus a is equal to plus or minus r or not, it depends on the series. And then so what you have to do is that you have to plug in the value of x minus a equal to r and x minus a equal to negative r. Those 2 points to see if you're gonna take those 2 value or not. And so as I say, the way that you're gonna find the radius of convergence is using the ratio test. And so the radius of convergence is going to be determined, and then the interval convergence. So the problem that you might be asked is that find the radius and interval of convergence. And the way that you're going to approach this is first find the radius convergence using the ratio and or the root test, and then you check back the series at the 2 ends. So basically you just plug in the value at the 2 ends and you determine if you're going to take that value or not. So you're going to know, is it the closed interval, is it open interval or closed interval? And so let's see the example to make it clearer. Find the interval and radius convergence of this. So first of all, you use the ratio test. So you're gonna put a n plus 1 over a n. This one is going to give us limit of n approaching infinity. So let's look at this part. If you replace n with n plus 1 in this term, what you're gonna have is that you're gonna have -2 to the n plus 1, x to the n plus 1 divided by n plus 1 square, multiply -2 to the n, x to the n over n square. And now this one is going to equal limit of n approaching infinity, n square over n plus 1 square. I can take it out of the absolute value because both of them are positive. Then you have -2 to the n plus 1 divided by -2 to the n. And you take the absolute value of that, so it's going to be 2. And then you have absolute value of x. Now, as n approaching infinity, this part is going to approach 1 because if you look at the highest power in the numerator and denominator, it's 2. It's square over square, right? So as n going to infinity, these two are going to approach infinity at the same rate, and it's going to be 1. And so this limit is going to equal to absolute value of x. We keep it. Yeah. So here you have x to the n plus 1 divided. Okay. So, and then you keep that. Yep. So here you have two absolute value of x, and to get it converges, if you go back to the slides here, you need the radius or whatever whatever you get from the limit to be smaller than 1. So this one is smaller than 1, and so you have the absolute value of x have to be smaller than half. So your radius of convergence is half. And now if you look at the series again, it's x to the n. So this one is centered at 0. So your interval convergence is going to be from negative half to half, but you're going to determine if you're going to take the two endpoints. So first of all, let's see for half, what do we have the series? So the series is going to become negative 2 to the n, negative 1/2 to the n over n squared, which is going to give us the series of 1 over n squared. And this one, now it's going to come back to the materials of midterm 2, where you're going to determine if the series is converges or not. Because if it's not converges, you're not going to take it in the interval of convergence. And so, as we look at it here, right? So the general form of the power series centered at A is Cn multiply x minus a to the n. So if it's written in the form of x to the n only, then you're going to rewrite it at x minus 0 to the n, right? Yep. So that's how you're going to know if it's centered at 0 or it's centered at A. So now come back to this series. It's a p series with p equal to 2. Therefore, you have p series with p equal to 2. Then you're going to have, this is convergent. Now, if you have x equal to half, then your series is going to become negative 2 to the n, half to the n, divided by n squared, which is going to give us the series of negative 1 to the n divided by n squared. And so this one is going to be convergence by alternating series test. And I mean, at this point, after you already finished midterm 2, these realization should be really quick for you, because you should be really familiar with those testing of the series. And so your interval convergence is going to take both endpoints. So is it clear to you what I'm doing here? Okay, cool. Let's go to the next questions. Okay, now let's try doing it on your own and see what you get from here. Don't look at the screen as I do it, but just do it on your own, and we're going to compare our answer together. So it's the same questions, but a different series. So what do you guys get? for this one. First of all, let's compare the limit that we have and see if we end up with the same result of the limit. So when I take the limit of n approaching infinity of the absolute value of a to the n plus 1 divided by a to the n, then I have that one is, so instead of having 2n plus 1 factorial here, I'm gonna have 2n plus 3 factorial, because you're gonna replace n plus 1 with n, replace n with n plus 1. So you're gonna have 2n plus 1 plus 1, which is going to give us 2n plus 3. And so if we continue to cancel out the terms, so here I'm gonna have a note here. If you have 2n plus 3 factorial divided by 2n plus 1 factorial. Now remember, the definition of factorial is gonna equal 2n plus 3 multiply 2n plus 2 and multiply until we have 1, which is going to give us 2n plus 1 factorial here, and then divided by 2n plus 1 factorial. So these two are going to cancel out, and this is what I have left in the numerator. So before I proceed to r and I, is it clear here how I get infinity? Yep. So it's infinity, and then cool. So that you have, so because the limit always equal to infinity, the only way that it's gonna be different from infinity and get smaller than 1, then you have x minus 1 is equal to 0, which means that it only converges at a point and your radius is equal to 0, and the interval only includes 1. Now let's get to 11.9 power series representation. So this is the part where I say how the calculators work, where you're trying to represent different functions in yes, r equals 0 if the limit is equal infinity, because when the limit equals infinity, and remembers your final terms of limit here, like here, it has to have something related to x, like x minus 1 or x minus 2 or just the absolute value of x. I don't really care, but it has to be the only point that is going to be converges, and this limit is different from infinity, is that this term is 0. That's why you have radius equal to 0, because it then in that case it only converges at a point, a single point. So the interval gonna have a radius of 0, and so the interval only includes 1 point. Oh, how did you get the interval? Oh, so the interval only includes 1 point because the radius is 0, right? So there's no interval because it's a single point. When it's a single point, you don't have a radius. And so if you look at this part here, when you just have 1 point here, the radius, if you only take this point, the radius is 0 because you don't span any of things here. It's a single point that you're talking about. So radius is 0 and the interval is only including the value of 1. Is it clear of how I get that? Okay, yeah, this is the way that you're going to represent that you have only 1, like the value of 1. Okay, now that's that, and then we're going to go to power series representation. So in this part, the main thing that you're going to do as the step that I wrote here is basically you just manipulate, differentiate, or integrate the sum of the trigonometric series. So basically, if you want to find a power series representation, a lot of them relates to one another by, say, if you have the function, the representation of 1 over 1 minus x, and you want to find 1 over 1 minus x squared, this one, you just need to take the differentiation and also take care of the negative signs. Or if you want to go to ln of absolute value of 1 minus x, then here you're going to take the integral of that and also take care of the negative signs related when you take the integral. So a lot of them relates together by just taking derivative or integration. So we have this theorem to get the trigonometric series. So during that time where you take the integral or differentiation. Then if your power series, like the original one that you want to take integral to arrive at your destined function, then if that power series have a radius convergence bigger than 0, then the function is differentiable on the interval of convergence. And so on like the open interval from a minus r to a plus r, or the interval that we say the open interval of convergence. Then you have f prime of x. If your series is starting from n equals 0, when you take integral, let's say this one is Cn multiply x minus a to the n. Then if you take the derivative of that, you're gonna have the series now starting from n equal to 1. And that series, when you take the derivative, is gonna be n Cn. So basically you take this n out, multiply Cn, multiply x minus a to the n minus 1. So that's the derivative. Now, when you take integral of that, the starting point doesn't change. It keeps at n equals 0 on whatever starting point that you have here. And that one is now equal to c plus the series of Cn multiply x minus a to the n plus 1 divided by n plus 1. And the final note is that the radius convergence remain constant when the power series is differentiated or integrated, but the interval convergence might not stay the same. So when you take the integral or derivative of the original functions that you already know, the power series representation, to arrive at your destined function, then you're gonna keep the same radius convergence, but to determine the interval convergence of now the new, like your destined function, you have to plug in the two endpoints again to see if it's gonna work. To see if it's gonna converges at the previous examples that we have. And some of the problems that you might be asked in this sections is that express a function as the sum of power series. So that's what I just say. You either integrate or differentiate of one of the functions that you already know and find the interval convergence. First, you express it by rewriting it in the manipulated form, which is integrated or derivative, and apply the fact that your multiplying factor is smaller than 1 to find the radius convergence. And also, you might plug in the endpoints if you're asked to find the interval convergence. Or you might be asked to compute the infinite sum of a power series. And so in this case, the second type of problems is where you do the reverse. So say if you have a functions, right? And they ask you to find a power series. So that's the forward way that you're going to usually do it. But if they ask you to compute the infinite sum of power series, you go in the other way around. You have the power series representation, and they're going to ask you to put it back into the original function. So say if you have some series here, I will use an example. X to the n starting on n equals 0 to infinity. Now, if you want to find the sum, you put it back into this form, which is 1 over 1 minus x. And so maybe sometime here you don't have x, you have its fifth, 1/5 to the n. Then this one is going to equal 1 minus 1/5. And so that's how you're going to find the sum of the power series. You put it back into the functions that you originally represented in power series. Some of the series that we already got so far is 1 over 1 minus x, which is what I just do. Then you have 1 over 1 minus x squared by differentiated. And you have ln of 1 minus x, which by integral it. And remember, here's a negative sign. And so ln of 1 minus x. Let's see what I'm reading here. Okay, so and then we have 1 over 1 plus x squared. Somehow I think I make a mistake with rewriting ln of 1 minus x here. But let's check if we have it. You have, when you take integral of 1 minus x dx, you have negative ln of 1 minus x plus c, which is going to give us, this one is x to the n dx, this series, and it's going to give me negative of that series. Oh, it's going to give me this series where I have x to the n plus 1 divided by n plus 1 with a plus c. And so this one is going to give me ln of 1 minus x is going to equal negative of that x to the n plus 1. Yep, I think I got it right. Okay, let's see. Okay, sure. That's what we have for so far, and I would highly recommend taking note of these power series representation, because that's gonna help you a lot when you start to do problems. You're gonna have a list to immediately look at, and so x to the n plus 1 divided by n plus 1. Let's look at what the chat room say. But isn't that ln has, yeah, that one is different, because where you have instead of 1 minus x, right, you're going to rewrite it as, so ln of 1 plus x is going to be equal ln of 1 minus negative x, and so in that case you're going to have it equal c minus this series of negative x to the n plus 1 divided by n plus 1. That's how you have negative 1 over there. You see what I'm saying? Okay. That's when you split negative 1 to the n plus 1, multiply multiply x to the n plus 1. Okay, let's see. Okay, so that's what we have so far. And again, a final note, just basically state it again. Taking derivative will shift your starting end from a to a plus 1, or from n to n plus 1, whatever you want to say, use a symbol here. And then taking the integral won't change the starting end. Now let's get started with the example. So let's see how many we have here. Yep, I think it's a good number. Okay, find the power series representation of ln of 2 plus x. And so that's when we're gonna use the original way to solve it. So we have ln of 2 plus x. This one is the integral of 1 over 2 plus x dx, right? And so we're gonna have, and so this series, how do we this function, we're gonna represent it in the power series. So we have that one is gonna be 1 over 2. You take the 2 out, because if you want to use 1 over 1 plus x, or just like 1 over 1 plus fx, any function of fx, you have to put it in the form of 1 plus. So you're going to take the 2 out, and inside you have 1 plus x over 2 dx. And now this is where we're going to use the representation of 1 plus fx. I think I also have 1 plus fx. If we didn't say it out, I'll write it here. So 1 over 1 plus x, or 1 plus fx, whatever you want to write it. You just replace the x with fx. You're going to have a series starting from n equals 0 to infinity. Negative 1 to the n multiply x to the n. And so you're going to have it here. It's going to equal the integral of half multiply this series 1 over 1 plus x over 2, which is going to give us a series starting from n equals 0 to infinity. Negative 1 to the n multiply x over 2 to the n dx. And now this is a constant, so we're gonna take the half out. And so when you take the integral of this, I'm gonna write this. This is an integral. So if you have an integral, negative 1 to the n for every single term in the series is a constant. And so you're gonna keep that. And what you're gonna take integral is only related to x. So you're gonna keep negative 1 to the n, but you're gonna take integral of this. Before I go any further, let me rewrite this x to the n over 2 to the n dx. Because you only take integral of anything that related to x to the n, and you keep -1 to the n over 2 to the n. So we're gonna have that one equal to the series of -1 over 2 to the n multiply x to the n plus 1 over n plus 1 plus c. And so to determine the value of c as well, we can plug in x equals 0. Because when x equals 0, this part on the left is equal to ln of 2. And that one is going to, when x equals 0, every term here is equal to 0. How do you know the value of x that you're going to plug in? Well, you look at the center of the power series. Here you have x to the something. It's not x minus a to the something. So the center is at 0. So if you plug in the value of x equal to the center of the radius convergence, then you're gonna have this series is equal to 0, which is gonna allow us to find what is the value of c. So this one you're gonna have c equal ln of 2, and so the power series representation of ln of 2 plus x is going to be ln of 2 plus half infinity n plus 1. You can also take this half inside, and you're gonna have, where did ln come from? Oh, it's coming from here. Well, when you plug it x equal to, here you have an equality, right? So you have this, sorry, you have this equal to this entire series. So when you plug in x equal to 0, you're gonna have the left hand side of the equation equal to ln of 2. And when you plug in x equals 0 on the right, is where you have this part is equal to 0, and you only have c left. That's how you have ln. So coming back to this series, you can take the half inside. You're gonna have ln -1 to the n, 2 to the n plus 1, multiply x to the n plus 1 divided by n plus 1. And so that is the power series representation of ln of 2 plus x. Before I go to the next example, is there any questions here? So basically, as I say at the beginning, the way that you're going to do it here is either represent your function, like your destined function, as an integration or derivative of one of the functions that you already know the power series representation. And then you're just going to plug in that power series representation, do the integral or do the derivative. And remember, when you do the integral or derivative, only take the integral or derivative of the part that related to x. So x to the n or x minus a to the n. Do not touch anything about the constant, because they are not changed when you take the integral, as you already know, or the derivative, as you always know about that part. When you take derivative of a constant, it stays the same, or like a scalar multiple of a function. It's gonna equal just the scalar multiple multiply derivative. Okay. Oh, I don't mean, what's the point of doing this to the functions? What does the power series mean? Okay, so what I did is that, the point of doing this, as I say, is that this is the way that we learn how calculators work and also advanced math work. So if you think about it in reality, when you plug in a number, say ln of 2 or ln of 5 in the calculators, the way that it's going to calculate is putting it in the power series. So basically a bunch of polynomials together and approximate that numbers for you. So this is the application of power series, at least in the calculator. In higher math level, when you do simulations and stuff, when you have very complex function, and so in those kind of thing, you want to represent that function in the graph. So using power series, it allows you to graph it closest to the actual value of the function. So we always thought that, okay, if you plug in exponential of 2 or say ln of 5 in the calculator, it's just gonna do ln of 5. But the calculators itself doesn't actually understand any other function except for polynomial. That's why we try to represent it in the form of polynomial, or we call power series representation. So that's like one of the applications and one of the most common way that we're going to use power series. Do you see what I'm saying? I mean, I haven't learned much about advanced math, as at least I'm in chemical engineering, but I can tell you this part have been used in field like chemical engineering when you try to solve like the equation, say, I think I remember it as the fluid equation, so the continuity equation and all kind of that stuff. Like you can solve the integral of 1 plus x to the 7. Okay. I think you can. Hang on. Integral of that. Oh, I mean, technically, I have no idea how to solve it currently, like at the moment. But yeah, I guess you're right. I don't know how to solve it. I mean, when you get to a higher level of math, I think you're gonna have some other techniques of how you're gonna solve it. But I myself have no idea how to solve it, honestly. Yeah, but before, I mean, it's not solving the integral, but maybe like represent something like ln of 1 plus x to the 7 or something. Then it's gonna be the integral of, say, 7x to the 6, 1 plus x to the 7 dx. Because here, if you plug u equal to the denominator, then this is your integral that you're gonna take, right? So if you put u as 1 plus x to the 7, then the du is going to be 7x6 dx. And so after that, then you're gonna, let's say, I think it's my example 5. Yeah, I think it's my example 5. But anyway, here, if you have 7 6 to x to the 6, you're gonna replace 1 over 1 plus x to the 7 by this power representation here. You're gonna replace just the denominator, and so you're gonna have 7, the integral of 7x multiply some other series, and so you're gonna put this x to the 6 inside that series and the 7 into that series before you take the integral. So because this integral includes this series and x to the 6 multiply one another, you're gonna put this x to the 6 into the series before you take the integral. So basically you put everything into one single series and then you take the integral of that. Do you see what I'm saying? Okay. So let me put in one of the extra slides and then we're gonna be able to, alright, let's me go back and escape, keep that, and then I'll add a new slide to this. Okay, let's write in here. So say if you want to represent ln of 1 plus 1 plus x to the 7, and so that one we're gonna have, that one is equal to the integral of this. So before I go to power series, is it clear so far of why I write it this way? Okay, so this one, now you're gonna rewrite this as 6 to 6 x to the 6 multiply 1 over 1 plus x to the 7 dx. And now this one is going to give us 7x to the 6, and this is a power series. And as I remember, it's going to be, this one is going to be the power series from n equals 0 to infinity, -1 to the n multiply x to the 7 to the n dx, right? Now, before I take the integral, I want to put everything into a single series. So what we have is that I have 7 multiply this series. Now I put x to the 6. No, because here you look at the integral. You have integral of this entire thing, right? And I told you, you have to take the integral of anything related to x. You have the x to the 6 here. That's why I told you have to put it into the series before you take the integral. Because if not, you're going to miss something. So say, just a very simple example. Before we have, if you have x to the x cubed, multiply x to the n. And then you take integral of that. What you're going to actually take integral of is basically n plus 3 dx. And then you take the integral of this entire thing, which is x to the n plus 4 divided by n plus 4, right? So when you take the integral, you have to take of the entire terms. If you only take of x to the 7n here, you're missing this x to the 6, which make your answer wrong. Do you see what I'm saying? Yeah, so basically here, that's why you have to put it into so you have x to the 7n plus 6 dx, and so when you take the integral, you're gonna have 7 this series negative 1 to the n multiply x to the 7n plus, so here you replace n with n plus 1, so it's 7n plus 13 divided by 7n plus 13 plus c. Okay, so yeah, remember when you go from here to here as well, you basically replace n with n plus 1. So wait, hang on, no, it's 7 plus 7 divided by 7n plus 7. So the power over here is only one unit higher than this one. So yeah, that's what we have. Okay, cool. Let's go back to our example 4. So example 4 is when you go the reverse way, when you put it in the power series into the functions that we have. Before we get any further, let me plug in the computer. I think it's right now battery. So before we plug it in the form, give me a second. This. So you're asking, before we plug into the form, we have to test the what do you mean by you have to test it? Can you be a little bit clearer of what you mean by you have to test it? Hello? Okay, so just make sure someone can hear me. Okay. I mean, okay, cool. Just want to make sure that I understand you right, but okay. So you compute the sum, and so from what we have so far, okay, cool. I mean, if you get a chance to make things more complicated, I mean, I'm actually very happy about you guys thinking about the problems. It means that you guys actually care about what you're doing and understand it, instead of just follow the procedures and be like, okay, what is the answer of this? Like, I don't like, when students don't actually question what they're learning, but this is a good sign. Anyway, I know, but like, if you look at that again, basically the procedure is very similar. That's why I always try to put in the step that you guys gonna do, like some of the problems that you might be asked and the step, because after you do a bunch of problems and you're gonna be like, okay, what exactly is the way that we're gonna solve these? And so that's when you're gonna look at these steps that you're gonna solve the problems. And so it's gonna essentially you're going to look at the problem and you're going to be like, okay, there's only one way you're going to solve this. It's just different functions that you're plugging it in. And so everything is actually super easy to understand, because I mean, it's like a lot of trouble to be at first as well when I learned this chapter, and I'll be like, okay, what the hell is it talking about? And then there's so many functions, and I've never heard about power series in my entire life. But then my professor is actually really good, as similar to Dr. Casher, where I think they're good friends with one another. But then they actually just put all of the way that you're going to solve it in just very simple strategy. And so when you actually solve a bunch of problems already and you look at their steps again, it's basically just the same thing and you're applying for different functions. That's why I would recommend you guys do a lot of problems, because when you already did that and you look back at these lines, you're going to be like, okay, this is exactly what you need, because you only need the steps and everything else is not really necessary. But anyway, yeah, like the textbook problems, my problems, I don't know if Dr. Cash would give you any other extra problems, but you can always go to the website of the math department. I think they have some things about power series practice. I remember that's my year. I have no idea about the year after that, but you can always email Dr. Casher about those files. I think she might have access to that as well. I currently don't have it with me because I leave all my materials in the US and I'm not in the US right now. So yeah, I mean that's a good score actually, 85, because I did look at some other people exam score for midterm 1 and it's not a very good one. And I mean 85 is a good one as long as you rock the final exam and maybe like check your work very carefully. Okay. So let's go to uh, let's go to, so here is the series that you already have the representation of. So we're gonna apply that for the question in example 4. Here you have n multiplied over 5 to the n. And if you look at the series that we've got so far, this is the only series that we have the value of n into the series. So we're going to try to put it in that form. N multiply x to the n minus 1, and the starting point is at n equal to 1. Now, this one will have the starting point n equal to 1. And so we want to write in the form of n equal to 1 to infinity, n multiply x to the n minus 1. So you're going to have n minus 1. Let's write this. It's going to be n multiply 1 over 5 to the n. But you need n minus 1, right? So you're going to take the 1 over 5 outside of the series. You're going to have n multiply 1 over 5 n minus 1. And so here it's going to give you 1 over 5. And so this one is the representation of 1 minus 1 over 1 minus 1/5 square, right? Which is going to give us, because this one is equal to 1 over 1 minus x square. So basically instead of x you replace it with 1/5, and so you're gonna have 1 over 1 minus 1/5 square, which is going to give us 1 over 5 multiply 25 over 16, which is going to give us 5 over 16. Yep, this is the way that you're gonna find the sum. And like that is, I don't know if you're gonna be tested something like this in the exam, because it technically is the same thing. Like you learn how to represent power series. You go from the function to the power series. When they ask you to compute the sum, it's going the reverse way. So technically, you should be able to find it. But yeah, I mean, you can be asked any kind of thing in the exam, right? So that's one of the type of other problems that you might need to know as well. So yeah, before I go to example 5, any questions here? Oops. Okay. The formulas is here. Excuse me. Okay, all good. So let's go back to, and we're gonna proceed to example 5. Find the power series representation of this one. And so the series here 2 to the 3x squared. Now, when you want to do power series for this one, I'm going to apply the 1 over 1 minus x squared. Why? Here I see the square. And so that's kind of like the only thing that I've have so far in the list. So I'm going to apply that one. But to apply that, I need a coefficient of 1 over here. So I'm going to do some manipulation to this. The 3x, I still rewrite that. And so you're going to take the 2 out of the square. So you're going to have 2 square be 4 multiply 1 plus 3x over 2 square. And now I'm going to apply this part. So it's going to be 3x over 4 multiply 1 over 1 minus 3x over 2 square, which is going to give me the series starting from n equal 1 to infinity, n multiply 3x over 2 to the n minus 1. And so now we're just going to put this entire term into the series and we're going to be done. So sometimes you have to take derivative, sometimes you have to take integral, but sometimes if you already have a form that is quite similar, like 1 over 1 minus x squared, then you can manipulate this one. What I did from here to here is do some algebra manipulations. And so there are 3 ways that you can solve these Pfeiffer power series representation problems. Is that you manipulate, differentiate, or integrate the functions that you're given. So here you have n, keep it the same. So you have 3 into this one. Where did the n minus 1 come from? The exponent, you just rearrange that. Oh, so this one is equal the series starting from n equal 1 to infinity and multiply x to the n minus 1. So that's how I get the n minus 1. So instead of x, here we have 3x over 2. So you basically take 3x over 2 to the entire n minus 1 power. Is it okay? So here you have this one. I'll rewrite this first so that you guys don't get confused with the step. So you have 3x over 4 multiply the series. And this one's going to be 3 to the n minus 1 multiply x to the n minus 1 over 2 to the n minus 1. And now when you put this thing in, you're going to have the series from n equal 1 to infinity. And you keep it the same. You have 3, because 3 into it, you're going to have 3 multiply 3 to the n minus 1, which is 3 to the n. Then you have x to the n. And then, 2 to the n minus 1 plus 2, because this 4 is 2 squared. So what we have is the series from n multiply 3n multiply x. Oops, why does it keep jumping? X to the n divided by 2 to the n plus 1. Yep. Yeah, don't jump ahead. So now, I mean, if I don't know what mistake you make in the exam, because I have no idea how you did it, and I haven't really looked at your test. But maybe this is one of the lessons, like don't jump ahead of time. Sometimes it's right, sometimes it's wrong. I've seen several cases when you write, but some of the time maybe like write them down, take some moment. Like, I mean, I can jump ahead and do it, but I don't want you guys to not understand anything. And I mean, if I make a mistake, if I write everything down, it'll be easier for me to track my mistake than, do that. So yeah, this is my power series. I remember the second answer you put in. Oh, shit, that's bad. Okay, so this is the power series representation of this function. So before I go to the last section of today, is there any questions so far? Okay, so if not, Kyrie, are you good here, or you want more more explanation from me? So just remembering those. Oh, one thing I also want to notice, you guys, just remember the formulas in the list, because I don't know about the world campus exam, but in my actual exam, final exam, they don't give us this list at all. You have to take note of them during your process of learning these materials, and you have to know it in the exam as well. And they don't give you any like cheat sheet or anything, so you have to remember all of these things. Yep. I don't know about world campus exam. I don't think you guys have a cheat sheet either, so just you have to remember them. And the things that you have to be careful, like if you know how to derive these, so like say if you go from 1 over 1 minus x to 1 over 1 minus x squared, then you know that you only need to take derivative. And sometimes you like, did you remember how I if you remember how I go to this part, go like how I check if I get ln of 1 minus x correctly. So if you know how to derive these, you should be in a good shape. And things you need to care about is like the starting point, like n equals 0 or n equal to 1, those kind of stuff. Yep. So I mean, it doesn't really matter. I think if you do a lot of practice problems, you'll be fine. And I don't think there are gonna be like a tons of these in the final exam. Just remember the part that even though it's like 40% of the exam, like the final exam materials, you also have some other parts that you also have things that you're gonna learn after today, which is like polar coordinates, parametric equations. Those kind of things doesn't have any kind of formulas. So that's gonna save your life. This is the only part that you need to remember something in the entire Math 141, because the thing in midterm 1 and midterm 2 you already learn, and those two are gonna comprise of 60% of the final exam. So it shouldn't be too bad. It's just gonna be a little bit more work, but you should expect that at the end of any kind of courses, it's gonna be more challenging than when you encounter it at the beginning. So yes. I mean, that's the rubric when I took the class. I don't know how Dr. Kasher distributed, but it should be like around that range, 60% from midterm 1 and midterm 2, 40% from the final exam materials. So you still have 60 points that you don't need to study at all because you already learned about it. And 40% is just that. So it's not that hard to achieve. So let's go to 11.10 and 11.11. Taylor and Maclaurin series. So Taylor and Maclaurin series is just the Taylor series and Maclaurin series are, first of all, these two series are different from the center. So the Taylor series is centered at A. A can be any number, but the Maclaurin series is centered at 0. And so the theorem that we learn here is that the Taylor series, when you have the series starting from n equals 0 of Cn x to the x minus a to the n, the theorem gives us the value of Cn, the coefficient in front of every term, is the nth derivative. So say if you have the first term, it's going to be the first derivative at a over 1 factorial. And when you have like the second term, it's going to be the second derivative of a at a over 2 factorial multiply x minus a squared. And it's the same thing for the Maclaurin series, but instead of a be the center, here the center is going to be 0. So it's going to be f0, the first derivative at 0 over 1 factorial, and the second derivative at 0 over 2 factorial. Then we also have the application of Taylor's inequality. So when you represent, say, like a function using the third degree Taylor polynomial, so say if you represent some function of fx using t3 of x, so you only expand this entire thing until you have x minus 3 to the third, something like that. Then this is the formula that's gonna allow you to find what is the error of that approximation. So instead of, say, this is the t n of x, so instead of expand it fully to the nth degree, you only expand it to the third degree. So this is the formula going to allow you to find what is the error of that approximation. And to do that, it's saying the error with that approximation is smaller than or equal to big M, with M be the maximum of the n plus 1 polynomial on the given interval of on the given interval. Yep. Let me go back now. Oh my god, what the thing going with the chat? Okay. Well, I mean, when a is not zero. Well, I mean, most of the time a is not 0. That's why I'm telling you, m is going to be the maximum of the absolute value of the n plus 1 derivative. So first of all, you have to find what is the n plus 1 derivative. And then you find the maximum value of that on the interval. So usually you're going to be given the interval, say, from -2 to 2, or like from -half to half, or things like if you don't have a center at a, you're going to have from 3 to 5. And you're going to find that maximum value of the n plus 1 derivative. And basically the n plus 1 derivative is just a function. And you already know how to find that maximum in Math 140, right? You use the first derivative. So say if you have the n plus 1 derivative of x is a function gx. And so you can take g prime of x and find what is the maximum of that. And it should be just like a quick a quick note on your draft paper, because you don't need to like show them the entire thing, like how you get this thing, like how you get that number, right? And then n plus 1 factorial, easy to understand, but then you also have x minus a to the n plus 1. This one is also the maximum of x minus a to the n plus 1 on the given interval. So say it should be easy to find, because you know x minus a, the absolute value of x minus a is always smaller than equal to d, which d is the radius of convergence. And so this part is always smaller than or equal to d to the n plus 1. And that is easy to find because they're going to give you the interval. So you only need to identify what is the radius from that interval, which is just, that interval, the length of that interval divided by 2, you're going to get the radius. Here is easy because when I take the class, if you look at these two kind of like these interval, and they usually also give you the center as well, so you know if that interval is symmetric or not. When I take the class, I was given an unsymmetric interval, so sometimes it get very tricky of finding the absolute value of x minus a, but that also make me understand like what exactly are those terms better. So if you just remember them, okay, just divide it and get the radius or something. Sometimes like people don't actually understand what they're doing, but then if you give them an unsymmetric interval, so say instead of 3 to 5 with the center at 4, they give you the center at 4, but they give you like 3 to 6. So if you look at here, it's 4 here, and this is 3, and this is 6. And so this is a non-symmetric interval, and sometimes it gets very confusing, but I don't think you're going to get that hard in the exam. I don't think she's going to trick you guys on that part. But yeah, usually you're going to be given a symmetric interval like 3 to 5, which is like 1 unit away from the center. So sometimes it's going to be that easy. And so you're just going to be, your absolute value of x minus a is just going to be smaller than or equal to r. So hopefully I haven't really confused you guys a lot on that. Now let's go to, solve the problem that you might be asked. First of all, find the sum of a series. What I said in the last section, put it in the form and calculate. Here you have the series of the Taylor series and the Maclaurin series as well. So there are more chances of you by finding like the sum using the power series. Estimate the maximum error when using the Taylor polynomial of n degree to approximate. So as I say, instead of using Tn with n going to infinity, sometimes people use T3 or T4, especially in the calculators. You don't need to do Tn because it's going to be a lot of calculations, and you only have that many decimal on your calculator screen. So sometimes they just use like T15 or T5, and the Taylor's inequality allows you to find the error relates to that approximation. And also the third one is use the Taylor polynomial at the n degree to approximate some other function. And here you already have the Maclaurin series of that. I think you also find these in the book. These are at center at 0. I would say do not freak out about like what if they're not center at 0. Since this is just like a few lectures, even though it's like a condensed course in the summer, you only have like 1 or 2 lectures on this part, so it's not gonna get super complicated, but you should know at least like the basic and the procedures of how to solve these. So I'm gonna go ahead to the example. Let's see, how many do I put here? Because I remember last night I put in something else. Okay. Example 6. Express the indefinite integral as the Maclaurin series. And so this part is pretty easy. You just plug in this cosine x expression into that and solve for it. So I'm going to go ahead and let you guys work on it. I'll get some water first. Express this one. So I'm just going to plug in and see what it gives me. Cosine x minus 1 over x dx. And so cosine x function is equal to the integral starting from n equals 0 to infinity. -1 to the n multiply x to the 2n over 2n factorial minus 1 divided by x dx. Now, to get rid of this 1, I'll try to expand this function to see if there's any 1 in this function to solve for it. And so I'm going to expand it in the way. If you keep this in a moment. Okay, sure. If you look at here, the first term in that series is 1. So if you expand that, you can actually cancel out that value of 1. So you're going to have 1 minus, let's go back, x squared, oops, x squared over 2 factorial plus x fourth to the 4th factorial minus x sixth to the 6th factorial until you minus 1 here divided by x dx. And so you cancel out the ones, and here you have whatever you have left here is basically, so when this term in the thing is when you plug in n equal 0, n equal 1, n equal 2, n equal 3. So you know, you can see the fact that the terms of n equal to 0 is cancelled out with this 1 here. So whatever terms you have left is just the same series with a different starting point at n equal to 1. So you have the series starting from n equal to 1, -1 to the n, x to the 2n divided by 2n factorial divided by x dx. So is it clear so far how I go from here to here? How I go from here to here. Okay, so now we're gonna, again, as I say, you have to account for this x down here. So put it in the single series before you take the integral. So you're gonna have the series starting from n equal to 1, -1 to the n over 2n factorial multiply x to the 2n minus 1 dx. And then you take the integral of that, which is keep all of the constant and only take derivative of things related to x, 2n factorial. And then you're gonna have that one is equal x to the 2n divided by 2n plus c. That's what we have. Is it what I have for? this part weird in the sense I didn't write it down. But yeah, that should be the answer of what we have here. Is there any questions so far with what I did? So basically you just plug in what is the representation of cosine x. Cancel some terms out because if you have x, that'll be easier to deal with. But if you have a constant, you should look for canceling out that constant. So let's go to example 7. Find the sum of this series. And so this is kind of the same thing. You try to put it into the function, knowing some of the power series. So here you see the power of 2n plus 1, and then you have -1. Oh, why did I move that away? Where did I move it away? It's right there. I mean, I just rewrite it as, because here, instead of, okay, cool. Okay, so let's go to example 7. So here you see -1 to the n, and then 2n plus 1, and then 2n plus 1 factorial, and the starting point is at 0. So if you look at these series in the list, it matched the entire thing here. You have the power 2n plus 1, you have 2n plus 1 factorial, you have -1 to the n, and then you have n equals 0. So it's going to be, you're going to try to put it into that form. So that series, if you look at the series for sine, you have -1 to the n, you have 2n factorial, and here you can combine pi and 4 together because they have the same power. So you have pi over 4 to the 2n plus 1, and it looks exactly like the series for sine x, except for x you have pi over 4 here. So you have -1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. So in this case, it's just going to equal, you have everything the same. Instead of x, you have pi over 4. So it's going to equal sine of pi over 4. And now it's going to equal square root of 2 over 2. So it might look very complicated, but if you know the power series representation, it takes 2 seconds to figure out what it is, right? Yep, I mean, that's one of the way that you can be asked. I mean, I don't know about you guys, but that's one of the way that I was asked during one of my class quiz. And I think it's really helpful because it actually opens up like all the possibilities of I was thinking like, okay, what do I expect in the exam? Do they expect us to know all kind of these power series? What degree that they gonna expect us to know? I mean, this is way harder than what you're gonna expect in the exam. But I guess Dr. Kasha is changing the curriculum this summer, so I have no idea like how hard she's gonna go on it. So I'm gonna put all kind of problems I know here just to make sure that you guys are ready. Okay, cool. Before I go to the last example of today, Kyrie, are we good on this? I just want to make sure you guys are on the same page with me. Sure. Let's go to the last example. Consider this function on this interval. So here, first of all, when you look at this, you have, see the question they're asking you. You given the function. You have the interval that they give you. And so the maximum of the derivative and also the maximum of x minus a to the n plus 1 power is going to just based on this interval. And they're asking you to find the Taylor series of the third degree t third x at a equal to 1. So you're going to first find the power series representation of this function. Then you're going to plug in n equal to 1, no, n equal to 0, n equal to 1, n equal to 2, n equal to 3, and find all of the coefficients and also the terms. And you're going to have like an approximate power series, no, not power series, the approximate representation of your function. Then the next questions always is going to be asking you to estimate the error related to that approximation. So let's first do the first one. So first of all, as I say, you write the power series representation of your function. So first of all, you have f(x) equal to x squared ln of x. Now, the approximation, oh, not the power series approximation, sorry. You don't write a power series representation of your function, but you use the thing that we learned about the coefficient of the Taylor series, which is the nth derivative of at a over n factorial. So, okay, so it's gonna be f prime of x is going to be first derivative. So it's gonna, so the first derivative is going to be 2x ln of x plus x squared 1 over x, which is going to give us 2x ln of x plus x. Now we have a second derivative. Oh, you also need f prime of 1 because you need the nth derivative at a. So you have, it's going to be 0 plus 1, which is 1. And then you have that one is going to equal 2 ln of x plus 2x multiply 1 over x plus 1. And now it's going to give us 2 ln of x plus 3. And so f double prime of 1 is going to be 3. Now you have the third derivative, which is going to be 2 over x plus, no, just 2 over x. And so the third derivative at a, which a equal to 1, is going to be 2. And you also need f. So as n equals 0, it's going to be f the zeroth derivative of a, which is going to be just f at a, which is going to give us f of 1 here, which is 0. So your third degree Taylor polynomial is going to be f of 1 plus f prime of 1 over 1 factorial. And I would highly recommend writing it in this form so that you guys don't miss any other terms or like plug in the wrong number. Over 2 factorial x minus 1 square plus the third degree derivative over 3 factorial x minus 1 cubed. Now you just plug in the number, which is going to give us 0 plus 1 over 1 factorial x minus 1 plus 3 over 2 factorial x minus 1 square plus 2 over 3 factorial x minus 1 cube. Now you can just, simplifying this with the algebra in the coefficient. So you're going to have 3 over 2 x minus 1 square plus 2 over 6, which is 1/3 x minus 1 cube. So is it clear so far of what I'm doing here? So basically you take the derivatives and you plug in number to find the coefficients. And then you plug in the general form of the Taylor series formula, and then you're just gonna have the approximation as they ask you. Now let's go to the second questions of finding the error. So this can be confusing. So wait, go back. Isn't that 3 over 4? Why is it 3 over 4? Because 2 factorial is 2. Because it's gonna be 2 multiply 1, right? Right. Okay, let's go to the next part. Okay, so here you said the error is smaller than or equal to m, or the maximum of the m plus 1 derivative on the given interval divided by m plus 1 factorial multiply the maximum of x minus a to the m plus 1 as well. Now we have, let's find n here is equal to 3 because you use t3x to approximate. So you're going to find the fourth derivative, which is going to give us, let's see what is the third derivative, is 2 over x. So the fourth derivative is going to be negative 2 over x squared. Right. And so the maximum of, so the absolute value of this is going to be 2 over x squared. And if you want to find the maximum of this, it should be easy now because your x is constrained between half and 3/2. So if you want the maximum of this, is where your denominator is the minimum. And so the denominator is minimum when you have x equal to half. So this one, m, or maximum of the nth derivative at x, is equal to 2 over half square, which is going to give us 8. And I would highly recommend doing it separately with every terms, because this is just like you just started the material. So writing down all of the terms will make you understand it better, and also remembers like what each of them means in the exam. So you don't need to like actually like look at the book and remember them by heart, but doing the practice by writing it down, you get the habit of thinking about it that way. So it's kind of like making it into your instinct, and it saves you time memorizing stuff. And now you have n plus 1 factorial, which is going to be 4 factorial. It's going to give us 4 multiply 3 multiply 2, which is going to give us 24. Let's see. Okay, so let's see what you're trying to find here. If you look at this fraction again, 2 over x squared, and you want to plug in the maximum of that derivative into it. So basically you want to find a maximum of 2 over x squared on this interval of x, right? And here you look at, this is just a fraction with a constant in the numerator and x squared in the denominator. So if you want 2 over x squared to be maximum, the denominator has to be minimum, right? Because if you divide it by a smaller number, you're going to have a larger number, right? A larger number overall. So that's why you want to plug in the the smaller value in the interval. Yeah, so you have to think about what is the maximum thing that you want to find. If you want to find the maximum of the denominator, then you plug in 3/2. But if you want to find the maximum of the overall fraction, you plug in the smaller number. And here the last term we have is maximum of x minus a n plus 1, which is going to be maximum of x minus 1 to the 4th, because a here is 1. Now if you look at this is 1, this is half, and this is 3/2. So the maximum distance from 1 is going to be, you plug in 3 into the last slide to get f. When you plug in 3 into what we calculated last slide to get, oh wait, you plug in 3? Oh, so in the previous slide we find the third derivative. So if you want to take the fourth derivative, you have to take derivative of the third one, which is going to, so you have f of fourth of x is going to be the third derivative, and then you take derivative of that, right? Which is going to be 2 over x derivative, which is going to be negative 2 over x squared. Is it clear of what we did here? Okay. Yep. And so, got it. Okay. So now here, let's go back to the last term, maximum of x minus 1 to the n plus 1. N plus 1 here is 4, and the maximum of the absolute value of x minus 1. Here, if you look at this, your interval is symmetric around 1, and the maximum, so if you look at the absolute value of x minus 1, it's basically just the distance from x to 1, and your interval, the maximum distance is half, either from the two sides of, it can either be half or 3/2, but the maximum of this, so maximum of absolute value of x minus 1 is half, right? So you're just gonna plug in here, is this part is going to equal half to the 4th, which is going to give me 1 over 16. And so now you just need to find your error is smaller than or equal to 8 over 24 multiply 1 over 16, which is going to give us 1 over 48. That is the maximum error when you use the third degree polynomial to approximate your x squared ln of x function. Hang on, I need to see the chat room. Okay, cool, I got it. Carrie, are we good here? Or you need more help? I want to clarify everything before I got off and turn this thing off. A over 24? Yeah. So this is 8. So m here is 8. This part is 8. This part is 24. And this part is 1 over 16. Okay, cool. So, final note. Review the exercise of power series representation from the previous section. I think 11.8 and 11.9. Know the general formula of the Maclaurin series and also Taylor series. But know the general formula of Maclaurin series of specific function, like things that we did in... Yeah, I have. After this slide. So we have cosine and sine, and also inverse tangent, and I think exponential of x. Know the general formula of any Taylor series, so any function. Do all of the problems in the book, and I would highly recommend you guys send the email to Dr. Kasha if you want more practice problems from the math department or from her in general. I don't think I have access to it right now, so I have no idea how to send it to you, but if you send her an email, that should be good. Or you should have a look at the math department website. And then next week is the recorded session. So next week I'll be away traveling. So I wouldn't be able to do the materials, but I'll try to put the videos up early so that you guys can have emails for me during the weekdays and also the weekends. Okay, so yeah, if you have any questions during that, and I guess you're gonna have a lot, but that's good. So send me email on that early. I'll try to get it on. If you haven't seen me do anything on like maybe Tuesday or Wednesday, shoot me an email and I'll get my work on that. I might have forgotten it, but I'll try to get it on by Monday. So these are the practice problems, and so as I say, the procedure is pretty much the same, but you guys have to familiarize yourself with the terms in the general thing and also remember the formulas of those kind of like series. That's everything I have for today. I guess I'm gonna have like after next week, and I think parametric curves and polar coordinates, I'm gonna have like the massive practice problems as well. So if you don't have any more questions, I'll see you guys next week. Have a great weekend learning power series.